All right, well, good morning everyone. Thank you for coming along and being with us these next 3 days. We're going to talk about the plant and equipment wellness way, and that's a technique to do enterprise asset management in a particular fashion with the aim of delivering success in asset management and, in the end, operational excellence for every company in the world. The aim here is to have one methodology, one way to achieve those outcomes. We're going to have 3 days together and we're going to cover the introduction to the concept, talk about the way the techniques themselves, and have a little bit of a discussion about how to use them, what issues we have in using those, and at the end give you an idea of the methodology to apply in your workplace. I call it a couple of names. One is Plant and Equipment Wellness, and that's the name of the book that this course is built around, and I call it the Plant Wellness Way as also. So I might use both names interchangeably. I like the Plant Wellness Way because the word way gives you an idea of moving from some point to a future better place, and that's the idea of this technique, of this methodology. Myself, Mike Sondolini is my name, and I'm an Australian, have been there all my life, 56 years old, and I've had a career in engineering from the shop floor right through to the office and running maintenance crews. And over the years, I've been trying to find an understanding of why we have so many problems in our machinery, in our companies. I went through a lot of hard times with my maintenance people trying to make our plant work well. And eventually I got to the point to say, well, look, what we've been taught and what I've learnt and what I've understood for 30 years doesn't actually work. So when I was 49, I sort of put that aside and began looking for answers to this worldwide problem of having reliable plant and machinery, because the answers weren't in what I was taught. I had to look somewhere else. And out of my search, some ideas began to form, and that's what the Plant Wellness Way is about. It's about these ideas that I think make a big difference. Maintenance is a small part of the answer. Other parts are going to be things like quality management, quality control, and even other aspects will be to do with Lean and Six Sigma. Process management, process as in the term, the methodology to achieve an outcome. So yeah, my background has been the trades, a fitter machinist. I built machines, I machined parts for machines. Then went into maintenance, went into mechanical engineering as a mature age student. I actually went back to university, got my honours degree in mechanical engineering, went out into industry and began applying my education and my experience. And over the following 20 years, I did work as project manager, as a maintenance manager, maintenance engineer. So came right through from building machines to designing plant, to installing plant, to maintaining plant. And as I say, at the end of many decades of searching and using previous solutions that never actually worked very well, I said, look, I'm going to put this aside and look for other ways of solving these problems. And so the Plant and Wellness Way comes out of those discoveries, I guess. Look, we are going to be here together for a few days, and any questions people have, please ask those at the time that we are covering a topic. It's easier to talk about things when the information's on the board than to go back. So feel free to ask questions at any time. The 3 days, the first 2 days, I guess, are the big days. We're going to cover the understandings behind the Plant Wellness Way. And again, there's nothing magical here. I haven't found anything new that wasn't there already. I've just packaged it in a way that makes more sense to achieve the outcomes of operational excellence. So we're going to cover the fundamentals right down to physics of failure, why things break. Going to talk about reliability and what reliability really is. There's a particular way to look at reliability, and it allows us then to control how we achieve it. Risk as in operational risk, the risk to our business in things going wrong because our plant isn't reliable. Cost of failure. In the end, this has to be a business benefits to what we do out of this. So money and making money is an important aspect of achieving reliability. It justifies why we want to do things in certain ways. I'm going to talk about how we've built our companies, how we've built our education, how we've built our world, as a matter of fact. And our world is a multitude of series arrangements, and because it's a series arrangement, it gives us some problems, and we'll discover those as we get to that. Human error is something else that has bugged me for a long time, because people are people. We are flesh and bone animals. We're never going to change that. Yet human error is our biggest destroyer of equipment, and need to understand what that is and how to solve those problems. In the end, we're going to look at the complete life of our operation, of our machinery, from the beginnings through to its disposal, possibly 20, 30, 40, 50, even 100 years away. So the life cycle concept is an important understanding when it comes to asset management. And the big issue, of course, is the final one for today, is reliability improvement. How do we take it from where it is today to a far better outcome? And we'll talk about those. Day 2, we'll actually talk about the 6 processes of plant wellness and describe what they are. There'll be some examples, and again, none of this is rocket science or new. It'll be a clearer understanding from our knowledge of the first day of how to apply these things effectively, and we'll cover day 2 when we get to it. Day 3 really is about packaging this thing, all these ideas into a solution, and understanding what we can do to create reliability from this foundational information that we're going to cover in the first 2 days. So yeah, we've got a couple of big days, and the day 3 is a shorter day, and hopefully more for discussion, more to look into things in more detail if we need to. Why do machines break? These pictures here are the result of something going terribly wrong. We don't want to go in these situations, and we want to find answers to all these problems. And what those answers are, we then want to make part of our business strategy, part of what we do every day in our company as the way we live our reliability practices. As it says up there, we get reliability by creating and building a thing that can do the duty and preventing its failure during its use. So I want to talk about the creating and the building side of things. How do we actually do that on purpose? Then once we have built in the right requirements, how do we sustain those forevermore so that failure doesn't happen? So we don't want to have any of this. If we see this, then our business process has failed. And because these are happening with us continuously around the world in every company, it says to me that what we're currently doing is not achieving the results we want, which is machines that are trouble-free for all their life. So I want to get away from these outcomes to a situation where they do not happen. They do not happen for the life of the plant, and that might be 20-year or a 40-year life. I'm going to design with that idea in mind. This isn't a matter of being perfect. This is a matter of achieving excellence, of moving forward all the time to find better results. And it may start off this way. Our first day applying Plant Wellness Way will be not too different from this sort of situation. But in the coming years, less and less and less, and hopefully no more of these things happen as we apply the right strategies and the right techniques. So we'll talk about these bullet points, and the first one is why things fail. We have known why things break for about, since the mid-1980s. Since the mid-80s, we've known all the answers. There's nothing that we don't know how to make our machines reliable. The engineering's there, the metallurgy's there, the science is there. There is no reason our machines should fail. So the problem is today is what we know we should do is not happening in companies. Companies are not applying the right techniques that have been around for 25 years. And it worries me that after 25 years of knowing the right answers, it isn't happening. And the challenge, I think, to business is to go and find the right answers, bring them into your company and lock them into place. Make it day-to-day stuff that everybody does. So the Plant Wellness Way is about driving that, about driving the right solutions into regular practice, and everybody does the right thing. Because the right thing we know, have known that for a long, long time, just isn't coming through our education process, isn't getting into use on the shop floor and in the boardrooms and in the offices and in the meeting rooms where people make decisions. And that's the thing that I see as our biggest constraint. The answers are there, they're just not being used. And this is the challenge that every company faces. And Plant Wellness Way is about facing that challenge with a solution, with a strategy and a process to achieve that. So we'll go through that, and I'll use my pointer at this stage. Fundamentally, why do machines break? Well, a machine fails not because the machine fails, because a part in the machine fails. So Plant Wellness Way is built around the concept of keeping every single part highly reliable, so that problems in the parts don't happen, so that our bearings don't fail, so that our bolting and connections don't fail. So if my parts don't break, my machine doesn't fail. So we're going to work very low level in the machine. So when it comes to the bearings in our motors, the motor is going to fail when the bearing fails. If the bearing doesn't fail, then the motor won't fail. And across all the parts in the motor, the same logic. When it comes to our lubrication, well, what is good quality lubricant? If the lubricant's good quality and always is good quality, well then it will last a long, long time. And so will the machines that it lubricates. Electronic components, same story. When it comes to the resistors and the various items in our electronics, what is the perfect situation that will give these things unfailing service life? Let's define those, let's make them very, very clear, and let's go and put those into place on our machines. And the same story with every bit of equipment, electronic, mechanical, instrumentation, it doesn't really matter. The thinking is they're all made of components. If the components don't fail, the whole assembly doesn't fail, and we get the reliability that we're looking for. Back to basics, because it all starts with an understanding of what is the conditions that create long service life. So our engineer, he designs a machine, he's in his office and on his computer these days, and back in my time I was on a drawing board, and I drew many of these things up myself in the years gone by. And the engineer, when he designs his machine, he says, okay, let me start somewhere. And he always starts with a straight line. And the assumption is that line is straight. It's perfectly straight, is what he thinks in his mind. Then he'll space off the distances he requires for the various sizes of components. Then he'll give the components a tolerance to work in. And in the engineer's mind is this understanding, hey, if everything's run perfectly as I've drawn here, then there is space to assemble things properly, there is space to put lubricant and keep the parts separated as they are in operation. And he thinks there's nothing that should fail this thing. Everything's in my head as it should be. And that's what the engineer looks at. He looks at the perfect world. Then he goes off and designs his machines along those lines there. Now these tolerances are very, very small. Now there's an example there. There's a human hair, and a comparison of that gap there to the human hair. We're talking about microns. There's not much space to play around with. So we have to respect the fact that there isn't a lot of movement available for our machine parts. So we have to maintain that life of that part within the constraints the engineer chose when he designed this. So when our parts get this done to them, then they're not going to last very long. This part's obviously under stress, and it's an exaggeration. Now, that's the whole point, to make it very clear that, gee, when I get a distortion like this, inside my bearings here, they are now also distorted. Huge amount of load on these components. Load above and beyond what the engineer allowed for in his design. Now this is going to fail in a very short time. So when it comes to running our machines, we also need to know what the operating envelope is. Now, what is the boundary of operation that we can run this plant in and get the long run of trouble-free operation that we're after? Again, nothing magical, but once we start stressing our parts, then they become distressed, and we get into situations where things start to break. Some examples of a distressed machine. Here we go, this particular pump set. The misalignment of the components causes these shafts to become bananas. The bearings, the mechanical seal, the components hanging off those shafts, they're under stress as well. They're distorted, deformed. Now when I press the button, this machine will actually turn. The machine will run, except it won't go very long. You know, it might go a couple of days, might go a couple of weeks, might go a couple of months. Yet this thing can run 10 years trouble-free, if it's done right. So whenever I see a machine failing very, very early in its life, up here I'm thinking, well, what's happening to it? What's being done to the machine to destroy its components? Because that's why they're failing. The parts are breaking. And they're breaking because they're being distorted, being overstressed for a number of reasons. So misalignment is a big one. Unflatness is a big one. Here, soft foot. A simple situation where this little gap there If we simply bolt that down without addressing the gap problem, then I will get a banana in my ram. Here, if I bolt down my pillar block on that base, I will actually squeeze that bearing. Now that bearing's meant to be perfectly round. Yet when I squeeze it, again, I press the button, that machine will go, except now under huge, massive overload conditions, and that bearing will obviously fail. So I have to know what condition this should be to have a long service life and make sure it's installed that way and kept that way for the next 20, 30, 40, 50, 100 years, whatever the case is going to be. Again, soft foot, if I pull that down, that foot will come down. The force we generate on this fastener will load up and distort that body. Now, we won't see it with our eyes, but our parts will be compressed. Here, my soft foot is an angular soft foot, so when I pull this down, I'll actually twist the body. You and I won't see it with our eyes. It's such a fine amount of movement, but it's enough to destroy those parts in very quick time. So I've got to know what fails the machine and control these, and make sure that whoever works on that machine knows that as well, and spots that problem and fixes it. Why do our parts fail? It's, again, worth understanding the situations that happens to our machines. Really, there's only two causes of failure of equipment. There's only two reasons our parts fail. One is they're overloaded at the atomic structure or metallurgical structure, or they fatigue. They actually get tired from use. This top situation here is an overload situation. So this is like on the gear teeth here of this particular pinion gear. The teeth have been snapped right off. Somewhere along the line, it's got one massive overload. Now, it was working fine, something's happened and bang, this fraction of a second situation where the material strength was perfectly fine, suddenly this load that was meant to be design load has increased hugely in this very small period of time, typically in a very small location. Now, when the engineer selects the materials for his parts, in his mind, again, he does a particular approach. This is stress, and this is just frequency. He asks the operations people, look, in this machine, what will you be doing with it? What weight of material, what sort of variety of situations will the machine be seeing? And from that, he gets an average load. He gets an average load and he says, okay, it'll be some sort of distribution from 0 to possibly 110% capacity, 120% capacity. So he knows the load from the operating requirements. He then says, okay, let me pick a material that is strong enough for the job. So he picks a material that is well clear of the load requirements it will see. And again, these materials typically come with a distribution depending upon where they're made. If they're made in a low-cost country, they might have low-cost materials. Made in, say in Germany, it'll be a better quality material. There's a distribution of capacity. This gap here is his factor of safety. So in the engineer's mind, he says, I have got massive capacity for any load situations. This thing should last a long, long time. So from his point of view, he's happy with that. In real life, what typically happens is when that part is in service and it's in the gearbox, and in the gearbox there is wear particles, bits of metal or bits of solids that get into the oil, then those wear particles that are typically fractions of a micron in size, 5 micron, 10 micron. When the teeth come together, the wear particle sits in the tooth. So in a very small surface area of our gear, in that very small area, when that wear particle gets trapped between the teeth, this load that was an average load, suddenly it moves up to here. And the load on that very small area, in a very small location, for a fraction of a second, becomes massive. And when these two overlap, we get the material failing. So this particular failure here is that situation there. In a very small area, huge overload, enough to start a crack, and that crack then propagates through the tooth, and the tooth falls off, and the machine's broken. The other way things the other way things fail is through fatigue. Where in this case, we have a situation of a number of overload scenarios, not full overloads, just the occasional increase, the occasional growth, for example by distortion. When I distort that, what's happening here is this localised load isn't the average load we originally thought. The localised load actually grows for a period of time because of that distortion effect on the parts. So this higher levels here began to actually fail our machines. And so you can see here, this bit of metal has these rings. And these rings tell us that there was a number of overload situations, this scenario here, that broke a metal for a small amount of distance. Over a number of cycles, this growth rings kept growing bigger and bigger and bigger until eventually there was not enough meat left, not enough material left of the body to take the next cycle, and the whole thing just broke. So this our parts fail in two ways. Either a massive localised overload that creates a crack in the microstructure, then propagates and breaks, or these multiple smaller high load situations that accumulate over time and we get a fatigue failure. So I can control these two factors. If I can control fatigue and control overload of our parts, then I've got a way to control the life of the machines. Because I can stop that, and if I can stop that, then they should not break. That's the whole thinking behind the plant wellness way. And wellness is literally that. Now, what is the conditions that give us a healthy life where things go well, where everything's fine and happy and the machine does what it's meant to do? As I say, this information has been around now probably 100 years. These particular curves here are fatigue curves. There's two types of materials we're talking about here. One is our steels, our ferrous alloys, which are the A curve. Then the non-ferrous, things like brasses and bronzes and aluminiums would be the longer curve. Interesting things when you have a look at what this curve is, and I learnt this in my university course. One of the things that mechanical engineers learn is this particular information here. It wasn't until I began looking for why things fail and trying to understand the science of failure that I went back to this particular curve, and it began to tell me a different story that I never saw before as a new engineer. What this curve says, so we take curve A here, curve A, it says here at very high stress, and this particular stress is the stress that fails our equipment. At very high stress, we don't last very long. You've got 10,000 cycles. But as the stress comes down, if I halve that stress, now I've got 1 million cycles. So what this curve says, if I want to have long life, if I want to go from 10,000 cycles to 1 million cycles to 10 million cycles to 1 billion cycles, then what I've got to do is bring the stress down from my parts. If I reduce the stress, then I get reliability. Because 10,000 to 1 million, I have made the plant reliable. I've got 100,000 more cycles there. Now with steels, it's interesting as well. Once I go below this threshold, this line here, once I go below that line there, it is infinite life on materials, on ferrous-based alloys. So the story is the same. If I want to have long service life of machines made of ferrous-based alloys, then I should be down in this zone here. I should be underneath this line here of infinite life. And when it comes to our bearings, top quality bearings, the designers of bearings actually design in this zone here. So bearings should last decades. Long time trouble-free, because that's what it's designed to do. So if our bearings are failing very early, as in a matter of weeks and months and even just a few years, what must be happening is they must be being driven up this curve here, because they're failing at sooner time than they should have failed. So when it comes to mechanical failure of our parts, then this curve plays a big part in why things are happening. They're designed to last a long time. They're lasting a short time. They must be being forced up this curve. And of course, life is being reduced. And the same with curve B, other alloys, other materials. This, of course, eventually goes to zero. So those parts, in time, will need replacement. But the story is the same. I reduce the stress lower and lower and lower, the longer and longer and longer my parts last. So if I can manage stress, then I have a way of controlling the reliability. And that's a big factor when it comes to the techniques we use in plant wellness. One of the techniques we use is precision maintenance. And that's about ensuring things are perfectly aligned, perfectly positioned, perfectly run to make sure we get the maximum service life before any problems begin to accumulate. This particular curve is a real fatigue curve. Again, this is for steels. And I wanted to put this one up because it is laboratory result data. It's the same story. For ferrous steels, we have this fatigue curve. Below about 0.5, about half of the ultimate tensile strength should go on forever. Should have no troubles at all with ferrous-based materials. Again, it just confirms when things fail early, we must be at the high stresses for whatever reason that stress is being caused. Remember, these parts, our parts don't care where the stress comes from. If the stress comes from an overload because of bad operating practices or a misalignment, the parts don't care. They're going to fail regardless of what caused the stress. All they know is, my stress is too high, I can't take it, bang, going to fail. So understanding that stress is the issue we have to manage helps us focus on what we've got to do to get this thing right in the first place. Now, I'm going to have a little activity here because I'm going to talk a little bit about this in the real world, and take a paper clip. There's a few things that we can do in an exercise. So I'm just going to hand out a couple of paper clips to you. And I want you just to break those clips for us. I'm going to get you to break 3 clips each. But count the cycles to failure. Okay, so I'll give you an example. So just take that particular clip here. And I'm just going to cycle this until it fails. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, 12 cycles. So again, you guys break the paper clips and count the number of cycles to failure. And please tell me what those cycles are, because I want to just begin having a look at what that means. Oopsie daisies. What'd you get, Bruce?
9, 16.
16, okay.
And I'm pulling it this way, right?
Doesn't matter.
Okay.
I just said break them, so please, any way you wish, it's fine.
9.
9 again, yeah, that's good. And there's no right or wrong here. It's not a matter of being right or wrong, it's just a matter of seeing what it means.
8.
Okay.
8.
You guys must have very similar techniques.
8.
Okay. All right, we have a distribution. You guys, because we've got that gathering, a very close grouping, you're probably doing things very similar to what it looks like. When we do this with a much bigger group, we get a wider distribution. Let me just put in the sort of range that we typically get. As low as 4 and often as high as 40. And a whole variety across those. Because all I've said is, look, please break the clip. And people go ahead and break that clip. So I've actually created a distribution now from a population of failures. I mean, this is actually the failure of a part. Now, what is that material there? Some sort of steel. Okay, so we're talking about material that our machines are made of. And when our parts fail, some will fail very early, and others of the same equipment, same material, can fail very late. The ones that fail very early must have had far more stress from somewhere, from the technique used to break them. The ones that take a lot longer to fail means that they're not being stressed as much from our previous slides. These ones here at this end must have been well up the curve compared to the ones further away when they were lower down the curve. What I want to do now is get you guys to do this a particular way. I want you to copy what I'm doing. And I'll just break a couple of these just to sort of see. So let me just show you what I do. So get both ends of the legs right out to 180 degrees, back to touch the fingers, and then cycle back. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, 18. Dear me, that's not right. 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10. 2 at 10, 1 at 18 at the moment. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 3 at 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, and you put those on there. We had 3 at 10.
I got 13, 16, and 17.
I got a 16.
36.
And I had, I think it was a 13. So,
And I did mine slower than you.
so give us those numbers again. Yes, give us
13, 16, and 17.
13, 16. Hang on, make that 16 and 17, wasn't it? And Bruce, what was yours?
I had 25 and 36.
Okay.
We probably all use different amplitudes.
Well, this is the whole point of exercise. If we get a very tight grouping, and typically I don't get a spread as much as that, I normally get a spread within 3 or 4, 2 or 3 of the main central point. It says to me that if I replicate this particular value every single time, let me just try that one more time. 15 that time. Now let's put that in there. So we've gone from a situation where we had a wide spread in a big population to a situation where we've got a much narrower spread. Recall at the beginning I just said, look, break a paper clip. And when you've got many people in a room, they'll break a clip in their own way. When I say, please do it this way, and I show them what to do, that distribution comes down very, very tightly. What we find is the same situation that we had already with Bruce's being fairly close, and then Mike's being further away. If this is where my technique gets the distribution, and we get somebody with a technique, the distribution's further out, then right away it says to me, we're not doing the same thing. Because if we were doing the same thing, you would get the same results as me. So it says, what have I done wrong as a trainer? Because I'm training you up to do the methodology as I want you to do it. No? I'm showing you what to do. So there's a few things here that we can pull out of this situation. This distribution of outcomes, because Mike's were not the same as mine, then either I have not got my message across clearly and I've got to retrain Mike, or Mike's technique, and definitely Mike's technique is different to what I was trying to get across. So if I want to get Mike to come back onto my distribution, I'm going to have to sit down with Mike and say, look, what are we doing that's different? Let me understand what you're doing, let me explain what I'm trying to get across, and then let's get these to come together. Because there's no reason that I cannot train Mike to duplicate what I want him to achieve. So by having it done this way, I've got a distribution of what there is without any controls. When I say do it my way, I'm installing a control mechanism. I'm saying, well, here is the technique to use. If we apply that technique and everyone does it the same way, we must get the same results. When we aren't getting the same results, that means the techniques are different, and if that's a problem, I have to address that difference. And that all comes from understanding the process outcomes. I mean, here I'm simply failing a piece of material on purpose. I'm intentionally failing this in a particular way. Because that way is defined very clearly and it's repeatable, everybody should fail within that distribution. When they are not, then I know there's a difference. There is something here that is different to what I have designed this process to achieve. So in a company, if I want to control the outcome of a process, I'm going to have to design the process to deliver the right outcome, prove that process indeed delivers the right outcome, and then if I want everybody else to achieve the same outcome, I've got to train them on that process. And when it comes to operations and maintenance, that process is called a procedure. Now, operating procedures is all about making this happen in the real world. If there's no instructions, if I just say do the job, then I will get many, many distributions, a wide number of outcomes. If I say do the job this way and this way only, then I have caused a narrow outcome of distributions. And if someone does the job and their results are not the same, their results are over here, then I know they are not doing it the way that it was designed to be done. That then lets me go and ask some interesting questions. Can I come and watch what you're doing? What are you doing that's different to what is in the procedure? Because the procedure will always produce results of that distribution width. You are off the distribution, there is something amiss here. Let us together solve this problem. So yeah, that's the whole point of this activity here. And of course, a couple of things is stress is the factor. Where I am on this curve, or on this graph, depends upon how much stress I put on those parts. Now, if the issue here is to make our machines more reliable, and Mike has found a way to do that. Look, Mike's results are way better than what mine were. So if reliability is the factor and minimising stress is what we're trying to achieve, then I've got to go to Mike and say, Mike, what have you done that is a better result than what I was doing? Because your results have longer service life than my results for producing. So I want to know the distribution for two reasons. One is to know, is the result where it should be? And when I find the outliers, when I find the ones that are producing better outcomes consistently than what we designed to do, I want to get those. I want to get that change, bring that change into my procedure, update the procedure to this better out result, and now make that approach the way we do things in this plant. That's the whole point of this particular activity. Recognise that stress breaks our parts and we can control the stress. And once we have a defined procedure, then we have designed a particular outcome. And when the procedure is not being done right, the outcome is different, and that difference lets us ask some smart questions. Let us push on. Slideshow. Where does the stress come from in our machines? Well, here's an example. The bearing's designed to be perfectly round within a very tight tolerance. And when things are run perfectly, as the bearing designer wants them done, then the loads are distributed across a number of rolling elements within the capacity of that material to last a very long time. Now, if the shaft is an oval shape, and here I've made the oval very exaggerated, what happens when it comes around to this position here is these elements are now being squeezed. Now, this oval makes the surfaces push together. So now for a very short period of time, my stress here, my stress that was here, goes like that. And I've got this fraction of a second overload situation because they actually push together like this. As it comes around 90 degrees, the same story again. These elements are actually being forced together for a short period of time. But I mean, this is happening in a 4-pole motor 25 times a second, in a 2-pole motor 50 times a second. This is how it's going. This particular graph there is what actually happens to our components. Let me just bring this down. This is the life curve of our roller bearing based upon the interference fit within that bearing. And what it's saying is this particular bearing is a ball bearing, and to get full life, to get a life of 1, the full design life, the interference fit required is a small preload of about minus 15 microns, about half a thou preload. So actually you've got to push these ball bearings together intentionally about half a thou at operating temperature to get the full service life. If I go 10 microns more, if I go from minus 15 now to minus 25, then I am down to 0.6 life. Another half a thou. Go another half a thou more, I'm down to 0.2 life. So when I have this situation of the situation here, where I'm pushing these things together more than half a thou, then I'm driving these ball bearings up and down that curve. These ball bearings and these elements here going up and down that curve, 3,000 times a second for a 2-pole and 1,500 times a second for a 4-pole. So I'm actually causing that bearing to fail from the high stress it gets from the out of roundness shaft. Because this is a laboratory result curve. This is telling us if I squeeze that bearing too much together, I will fail that bearing much, much earlier than its full service life. And if I've made the bearing too loose, if I actually put a gap in there on purpose, I'm on this side of the curve. I'm still losing a great deal of service life. So when it comes to machines with bearings, I have about 10 microns, 15 microns to play with. I've got half a thou to play with. And I've got to be in this zone here for the entire operating life of that machine. Now I've got to build a process in my company to make that happen. I've got to make sure that every single bearing is in its zone for full service life, and we do that on purpose, not by accident. Because by accident I could be too much overload or not enough. So I've got to design a process to make sure the right thing happens every single time, because when it's wrong, either too much load, not enough clearance, the machine, she fails too early. And that's how our machines are designed. That's the way they all work. This particular curve here is the degradation curve for bearings, and we can actually measure our bearings failing. We know that we can detect the vibration signature, we can detect temperature rise, we can detect audible noise. As the bearing begins to fail, it tells us it's in trouble. We first pick up evidence of a problem at this particular P point, the potential failure point. That's the earliest point in its bearing life that we can detect some evidence of it no longer being in good condition. We do that with things like vibration analysis and ultrasonic energy detection. So we have some very high technology solutions here to find that point. If we wait longer, then our bearing degrades down to the point where we can actually touch the bearing and she's hot. We know she's close to failure. If we wait a bit longer again, we get to the point where we actually hear the noise. The bearing starts to squeal. So it comes down this degradation curve. Condition monitoring, the methodology of that is to find this P point as early as possible, to find where the trouble is becoming evident, and then before this bearing actually causes a problem is to replace the bearing. The problem starts at the F point, the functional failure point. By the time it's here, that bearing is unsuitable to remain in service. That machine is in trouble, in serious trouble. So we want to have this PF window. The sooner we can find the P, the longer the time we have to plan for the job and replace it before it becomes a breakdown. When it comes to maintenance strategies, we use this curve in a couple of ways. I can maintain my bearings at this point here, but this requires high technology, well-trained technicians, very expensive approach, but one that's very, very practical. It works well, many companies apply it. Or I can have a technique where I actually wait for the bearing to fail, and at this point here, when it becomes obvious to the operators, I can maintain the machine at this situation too. But if I maintain a machine close to the F point, then it means internally in the company, I will have to have the parts. Got to have the parts on site. Whereas here, if I find it at the P point, and this is a 2-month window, then I can order those parts in that 2 months. So this level here, this point here, and this technique here of high technology condition monitoring, I can have less spares because I've got time to buy those spares in. If I have low tech condition monitoring at this end here where I'm using my body sensors, I'm using low cost equipment like here, then I've got to hold those parts very, very close. Or they're a phone call away and the car's here in a couple of hours. So I don't mind how you do your maintenance, but understand, depending where you are, you have to approach it in a certain way. One way is more generous, but also more costly. This way here is less time, but it means you have to carry the risk and manage that risk in a different way. The whole point being is once the thing gets stressed, it's on its way down. Once it begins to fail, there is no way of stopping that. And at least I can reduce that stress. If I can take that stress away from my parts, then I'm having less likelihood of failure. So yeah, this curve becomes very important in our choices and certainly in the condition monitoring techniques we choose to use. Some of these stresses also come from the way we operate our plant. It's a particular drag line. It's from a company in Australia. This is a laboratory trials, or I guess more of a scientific experiment. They actually put load cells on the boom here, began measuring the stress in the boom depending upon the different ways the operator ran that machine. And you can see the three different shifts, shift A, shift B and shift C. And here are the outputs of the various shifts. And shift B is the best output by a long, long way, 50 million tonnes in this time period. But he also had 5 breakdowns. Shift A had 30 million tonnes and 3 breakdowns, and shift C, 28 million tonnes and 2 breakdowns. What we don't have here to be able to say what is the right thing to do, I can't tell you which is the best approach to take until I know what each breakdown costs. Because this guy, who does 50 million tonnes, he makes the machine work very, very hard, and he busts it many, many times. But he makes so much more production that maybe it pays for those breakages quite comfortably. This might be the way to run the machine. Run this machine till it dies, work it very, very hard, then repair it. Could be better than running it more gently and having less breakdowns and having less production. I can't tell you what the best thing to do is until I know what the cost of those failures are. So this guy, I suspect in this company, he's called the gun. He's the gun operator. This guy is the one everybody looks up to because his numbers are great, huge output. My trouble as a maintenance person, as a person in charge of asset management, is that the smart way to run the business? And I can't tell you the right way until I know the cost of the repairs. And if the repair cost is more than the production cost, the value he makes, then that is not the way to run the machine. But it might be. So now the financial implication of breakdowns is important. Because I don't mind having breakdowns if it makes money for the company. But I better be sure it does before I justify and train everybody up to do it this way here. Because if this way is the most costly way of doing it, then I've got to not go there. That's the wrong thing to do. So money is very important in maintenance because it does, without the business implications, the financial costs, I cannot tell you what the right thing to do is. And so in plant wellness, one of the things that we push very, very hard is dollars and cents. We don't make a choice until we do the financial modelling. Now, what is the best business choice to make? Because here are 3 choices, any one of which might be okay. Which one is the right choice, I can't say until I see the money. So financial modelling of our maintenance choices in plant wellness is a major requirement to confirm before we do anything, hey, this is going to make money, not lose money. Because right now, I don't know what the right answer is here. I just know that one is very expensive for breakdowns, but it also makes a lot of production. But until the payback is there, I can't tell you. So yeah, we run our machines and they get one overload and one overload, you get away with that. Another overload, you get away with that. Eventually, if you have too many overloads, we have a fatigue situation, and of course that final overload, the death overload, bang, it goes to 0. So, and none of that had to happen. We could have had a machine running a long, long time trouble-free, except for some reason it's got a stress. The stress has been induced in whatever way. Once the stress is there, the parts will fail. So I want to be understanding what is causing the overload to create the stress that has now reduced what could have been trouble-free operation for a long time to a breakdown. And this slide's encompassing, I guess, the whole of the previous slides. This is a plant in operation. This is equipment that we're using to make our product. So we begin here at time 0, and here's our factor of safety. Everything looks good on paper. No reason we should have a problem here at all. Trouble is, you begin operating the plant, and for some reason, in a localised area, in my little localised small surface area, I get an overload. Then another overload. And that overload could be from operating practices, misalignment, wrong interference fit. There's a whole bunch of reasons that our parts get stressed. And as each part has a stress, we lose a little bit of life. A little bit of life disappears every single time we get to these high points here. Eventually we have so many of these overloads accumulate that the material is now fatigued. It is no longer at the strength it was, it's a reduced strength. Eventually one day comes where the two overlap. The fatigue left in the life left in the part, and the overload it sees on that particular day, she goes down. When it comes to maintenance, what we try and do is find this point here. The point in time where the two curves are not yet overlapping, and replace the part and restart this curve back at the highest value again. So this time here is our part replacement time. It's what we do preventative maintenance for, and we want to fix that date. And if we can get that date right, then we simply renew the part, restart it again, and off we go with, again, much time without problems. If we miss that date, then our curves begin to overlap, and we have more and more breakdowns. Now what it means is eventually every single machine will need to be renewed. Every single part in our machines are suffering up some sort of cycle, some sort of operating loads, some of which are high, some of which are normal. Eventually in time, over the years, they will accumulate. So maybe over 25, 30 years, this scenario typically is going to happen with every machine. So one of the things you want to allow for in your capital expenditure in equipment-based plant is to replace your machines after a certain period of life, because every single part in that machine will be suffering in this situation, and we can't replace all the parts at every single time. So at some point in time, we're going to put a new machine in there and do away with the old machine. But until then, while the old machine's there, we replace the parts that wear out on a regular basis. Now, it doesn't mean we don't have a failure. This particular situation here doesn't mean we have no failure up until that point in time. This is gradual fatiguing by use. We can still have a situation where there's an instantaneous load and bang, she'll fail. That broken gear tooth is an example of, even though it's a brand new machine, still break gear teeth in a brand new machine from a high instantaneous load. So we have this curve down here where this is the machine life. At any point in time, it can see very high stress for whatever reason, and that can cause an instantaneous failure. So some parts will always fail at an unknown time. There will always be some sort of failure from these unknown and unforeseeable high stresses. Eventually, every single part will age, will tire, and so as that part gets older, the chance of failure increases with age. So we get this situation here where even a brand new machine can be failed early because of this unexpected failure load, or eventually every single machine will wear out and have to be replaced. So this curve tells us in time things will fatigue and get old, and up until that time opportunity is always there for things to go wrong. And again, you want to minimise this opportunity. You want to minimise two things: the stresses these parts see and the situations that allow those stresses to arise. The method we use these days is called physics of failure. There's actually a technique that the good manufacturers are applying where they model the parts in their machines either on computer or as a prototype, and literally over here they have a look at what sort of loads is this part going to see, and they'll look at things that will destroy the item intentionally. Let's try and understand why these things fail. So temperature, humidity, shock, cycling, the cycling of the part. They can actually understand why our parts fail. What materials do we select? What sort of design shapes do we apply to minimise these stresses? And this can all be done very early on in the design phase. From that, we have a look at what situations those parts will see in the real world, understand what range of stresses will affect them, work out the reliability of this equipment based upon these different scenarios, these what-if scenarios. Sensitivity analysis is the other word we use here. So from our, laboratory and engineering knowledge, we come up with some choices. There's always a design trade-off. We're never sure what sort of costs people are willing to wear. So we're going to design a machine that we can sell, that people are willing to buy, but in an understanding of what its limitations are and how to run this machine so it has a very long service life. So the good manufacturers are applying the best technology, the best science, the best engineering to come up with a selection of materials and designs that maximise the service life of their parts. And that technique is called physics of failure. And we want to have companies that apply these techniques. We want guys to have thought through why these parts fail, what situations can cause these random lows to suddenly appear, and prevent those situations in the design of the machine. If we can do that at the beginning, then we have designed a long service, trouble-free machine. So yeah, we have the answer. And I said before, there's nothing here that we don't know what to do. We know the science, know the engineering, but it's just not being applied as widely as it should be. Now, physics of failure takes this stress concept and works around how do we find what causes the stress. What we do, quite literally, we say, okay, when it comes to our structure, our material structure here, our materials are going to be made up of a microstructure of some sort of type, made up of atoms and arrangement of atoms of some sort of type. Now, once my bonds break, that thing fails. Once I get a crack in my if a crack starts in the microstructure, that crack moves on down through the microstructure. Eventually, the whole thing fails. So if stress is the problem, if overstress is the problem, then I've got to work out where that stress comes from and control the causes of that stress. And that's what this particular table is about. Sitting down and having a look at the material that we've got, what can cause that microstructure to fail? What sort of situations will it get a shear stress? What sort of situations will cause a cyclic stress? What situations cause the part to melt? What can cause it to be ripped apart? Because I don't want any of these to happen. I want to understand when this part is in operation, in that machine, in this company, in that scenario, what can make it fail and not allow those to happen. So I'm going to take what can make it fail and work out what prevents that failure and put that prevention into my procedures and train my guys up to the procedure in a way that makes sure that they do not induce these situations. So this particular table is all about being negative in a way that helps us understand how can I prevent this failure of that microstructure? What is it that will prevent that, make that part of our process of running that machine, of maintaining the machine, of even procuring the machine? You know, when it comes to manufacturing of that machine, what sort of manufacturing issues are going to then lead into failure of a machine in operation? So the metallurgical selection, if it's a casting, if they cast it poorly and there are holes and gaps and cavities in that casting, that's going to lead eventually to failure of my machine. So now I want to understand across the whole life cycle where the troubles that I will have to suffer and solve can come from, and then intentionally build the process to prevent those in the first place. So there's quite a few reasons that our parts can fail, and this is the whole purpose, is to take a table of the things that can go wrong: unbalance, misalignment, shrinkage, expansion, hammer, pressure hammer from our process. If our process has a lot of pressure hammer, then that will lead to failure. So now I've got to design a process where that hammer is prevented, where if that can't be prevented, then I'm monitoring the effects of that stress on my parts. So when it comes to deciding our maintenance and our operating techniques in plant wellness, we actually look at the worst case scenarios. Understand what they are, because not all these things will happen on every single machine. Only a range of these particular problems will occur. But knowing what they are, I can now design a process to address them and to prevent them. So when it comes to maintaining this part in our gearbox, we're going to say, okay, what can make that tooth fail? And from our list, we'll get maybe a dozen things that can make that part fail. That dozen, we then look at the strategies to prevent those. Operating, maintenance, even initial procurement, initial selection strategy. So I want to understand how to protect this thing from failure and build the protection into what we do every day in this company.